Whenever you have to join a circular pipe to the vertical plate, then you can use the circular fillet weld here. So circular cross section is shown here, and over the entire circular area we have fillet weld whose throat size equal to 0.707 times h, where h represents here the leg size. So this size is same as equal to the throat size t. The given circular pipe can be subjected to torsion or can be subjected to pure bending moment. So either we can consider here a case of pure torsion or a case of pure bending moment, or it can be supplied to a transverse vertical load can be acting on the tip of the pipe that will be act as a cantilever with the load at the free end. But that case we'll discuss later on. First of all, we'll discuss two cases when we have a circular cross section of a pipe and is subjected to the pure torsion, or we have circular cross section, it is subjected to a pure bending moment. So as per the standard symbol, you have to show here the overall welding, that is a circular welding, and we have a fillet weld. You have to mention the size of the weld here. Let's say equal to 6 mm is the size of the weld. When it is subjected to pure torsion, then we can use the torsion formula. According to the torsion formula, we have twisting moment equal to T divided by polar moment of inertia J by tau divided by R. Or we have maximum value of the shear stress will occur at the outer pipe ring, that is at a radius equal to capital R, where capital R represents here the radius. This thickness is very small, we can neglect it and we'll take the value of R. To find out the value of maximum shear stress, we require the value of J, that is the polar moment of inertia for this thin ring. So you need to know first here what is the polar moment of inertia of this thin ring, and if the same circular rod is subjected to pure bending moment, then we can use the flexure formula. The standard symbol is used again. We have to show here circular because we have the weld all around, and this one is a fillet weld, and you have to mention the size of the leg size, that is equal to 6 mm. Again, for example, I am writing here 6 mm. You have to write here value of h. So by flexure formula, we have m by I, where I is called as the moment of inertia, is same as equal to sigma b divided by y, where sigma b is a bending stress, will be the normal stress, and the value of sigma b will be maximum again at the outer fiber, and the outer fiber is at radius equal to R. So here we need to calculate the value of I. So we want to calculate for thin ring what is the moment of inertia and what is the polar moment of inertia. So we'll first introduce here the concept of moment of inertia about the x-axis, moment of inertia about the y-axis, moment of inertia about the z-axis. The moment of inertia about the x-axis is given as a perpendicular distance square that will be equal to y square multiplied by dA. Moment of inertia about the y-axis is given as perpendicular distance square, that is x square dA. And the moment of inertia about the z-axis is given as integral of r square dA. If you consider here any point or any differential area, then it can be located at this point. So this distance is same as equal to x, this distance is same as equal to y. These two distances are perpendicular to each other, and this one is the shortest distance for z, that equal to r. Here r square will be equal to x square plus y square. Since we have r square is equal to x square plus y square, so we can replace here iz, that is r square we can replace, and we have iz will be equal to integral of x square plus y square multiplied by dA. We can write this integral iz as integral of x square dA plus integral y square dA. That is, we have iz is same as equal to ix plus iy. This one is the famous perpendicular axis theorem. So we can apply the perpendicular axis theorem. In that case, we have iz is ix plus iy. This value of iz, that is the second moment of area iz, which one is also called as the polar moment of inertia, which is represented by J. So J here is called as the polar moment of inertia. That is the second moment of inertia. So in this case, we have J is same as equal to Ix plus Iy. For symmetrical figure, that is, this annual ring is symmetrical about x and y axis. So in this case, we have Ix is same as equal to Iy. That is, we have the value of J will be equal to either 2 times of Ix, or we have J is equal to 2 times of Iy. So only we have to calculate the value of J, then Ix will be J by 2 and Iy will be J by 2. The area of this thin ring is A will be equal to circumference multiplied by thickness. Circumference in this case will be equal to 2 pi multiplied by r, which one is the radius of the ring, multiplied by thickness t. T we can replace as 0.707 times of h. So we can very well calculate the polar moment of inertia J for elemental ring. This time the value of r is remain constant, so we have integral of r square multiplied by dA. R square is constant that can be taken outside. In that case, we have simple integral of dA. Integral of dA is the total area of the ring, so it will be equal to r square multiplied by the circumference, which one is 2 pi r multiplied by thickness t. So polar moment of inertia is simply equal to 2 pi r square into r is r cube multiplied by throat thickness equal to t. So remember this formula for polar moment of inertia. In that case, we have Ix as well as Iy is equal to J by 2. That is equal to pi into r cube multiplied by thickness t. So this formula is important for us. So whenever the shaft is subjected to pure torsion and it is a fillet weld all around the weld, then we can use the torsion formula T by J equal to tau by R, or the maximum shear stress divided by capital R, where we have J, the polar moment of inertia, is 2 pi R cube multiplied by the throat thickness equal to T. And if it is subjected to pure bending moment, then you can use the flexure formula as M by I equal to sigma maximum, this one is the normal stress, divided by the radius R of the shaft, and the value of I is same as equal to pi R cube T. If the circular fillet is used to weld a circular pipe on a plate, and we have a point load is acting vertically downward, in that case this area, which one is a fillet area, is subjected to the force F plus we have bending moment at the end. So at this point A here we have maximum bending moment. So if we draw the bending moment here, then the bending moment at point B will be equal to 0 and it increases linearly, and the maximum value of the bending moment is same as equal to F multiplied by L. So the given fillet weld is subjected to bending moment plus additional 1 shear force will act. So here this force will act in a vertically downward direction, plus we have the bending moment will act equal to M. So two types of stress is produced. One is the normal stress, that is the bending stress due to the bending moment, and one is the primary shear due to the force F. The area resisting the shear will be equal to the circumference, which is equal to 2 pi r multiplied by thickness t, and the thickness t is same as equal to 0.707 times h. The state of a state can be represented by one stress that equal to sigma, which one is maximum bending stress, and one value is the shear stress tau, that equal to tau xy. The stress along the y direction will be equal to 0. So by flexure formula we can calculate the maximum value of the bending stress. So we have maximum value of the bending stress is sigma max is same as equal to M into R divided by I, where I is moment of inertia is equal to pi into R cube into the throat thickness T, and we have transverse shear stress tau is equal to the vertical force F divided by the resisting area A. That is, we have force divided by area is circumference is 2 pi r multiplied by throat thickness equal to T. So since here two stresses are acting, we can calculate tau max. So we have tau max is given as under root of sigma x minus sigma y divided by 2 whole square plus we have tau xy square. But the value of sigma y is 0. In this case we have sigma x is same as equal to sigma. So we have sigma by 2 whole square plus we have tau xy square, that is tau square. In this fashion we can calculate tau max. And if we want to calculate the value of sigma max, is sigma x plus sigma y by 2, that is same as equal to sigma by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau xy square is same as under root of sigma by 2 whole square plus tau square. So three type of problems will appear in the case of circular fillet. In this case the pointed force is acting at the free end of the circular pipe. Second case we have the torque is acting and this torque is remain constant. So in that case we can calculate the value of tau max as T, that is the torque multiplied by radius divided by J, where J is equal to 2 pi r cube into T, where T is the throat thickness is 0.707 times H. And if it is subjected to bending moment, then the maximum value of the bending stress we can calculate as M into R divided by I, where I is the moment of inertia will be pi r cube into T. A circular shaft of 50 mm diameter is welded to the support by means of circumferential fillet weld as shown in the figure. It is subjected to torsional moment of 2500 Newton meter. The value of T is given as 2500 Newton meter. Determine the size of the weld. Value of H you have to find out. The permissible shear stress in the weld material is 140 megapascal. So we have diameter D is equal to 50 mm. Therefore we have radius equal to 25 mm. Size of the weld you have to calculate. Torque applied is T is equal to 2500 Newton meter. And the value of permissible shear stress, that is tau allowable, will be same as equal to tau is equal to 140 megapascal. We require the value of J here. The value of J is same as 2 pi r cube multiplied by throat thickness equal to T. If we use the torsion formula, which is given as torque divided by polar moment of inertia, we have tau, which one is maximum value of the shear stress, divided by capital R. The maximum value of the shear stress will be at the outer fiber. So in this case we have tau is equal to torque multiplied by R divided by J. Torque you have to take in Newton meter is 2500 is Newton meter. So you have to multiply by 10 to the power 3. Radius we are having 25 divided by the polar moment of inertia is 2 into pi into r cube. R cube is same as equal to 25. So we have 25 cube. And we have shear stress is equal to 140 multiplied by T. So from this we can calculate the throat thickness. We have throat thickness is 4.55 mm. We have throat thickness is same as 0.707 multiplied by leg size H. So we require the leg size equal to 6.43 mm. The figure below shows a circular fillet weld of leg size equal to 8 is subjected to pure torsion of 100 Newton meter. The shear stress occurring at the throat of the weld you have to find out if the diameter of the rod is given as 40 mm. So this time the diameter D is equal to 40 mm. Therefore we have radius R is equal to 20 mm. We have leg size H is equal to 8 mm. Tau we have to calculate. Since a case of pure torsion, we can apply a torsion formula, and for that we require polar moment of inertia, which is same as equal to 2 pi r cube multiplied by throat thickness equal to T. And we have throat thickness T will be same as equal to 0.707 multiplied by leg size equal to H. So if we apply the torsion formula, in that case we have T by J is same as equal to tau by R. Shear stress we have to calculate, so we have tau is equal to torque multiplied by radius R divided by polar moment of inertia J. Torque applied is 100 Newton meter, we have to use in Newton mm, is 100 into 10 to the power 3. Radius R is equal to 20 divided by 2 pi R cube. So we have 2 pi R cube, R is equal to 20, that is 20 cube. Throat thickness we can replace as 0.707 multiplied by the leg size equal to 8. So in this case we have shear stress is produced is close to 7.03 megapascal. A very straightforward question. You have to just remember the value of J, which is equal to 2 pi R cube multiplied by throat thickness equal to T. And if you are given the leg size, then the throat will be equal to 0.707 times H. A welded joint is shown in the figure is subjected to torsional moment T. The diameter of the solid shaft is 50 mm and the leg of fillet weld is 12.5. Value of H is known and the diameter is known. Allowable shear stress is 75. Maximum value of T you have to calculate. So we have given the diameter T is equal to 50 mm. So we have radius R is equal to 25 mm. We have fillet size, that is the leg size, equal to 12.5 mm. Allowable shear stress is tau is equal to 75 megapascal. And we have to calculate torque. So in this case also we required polar moment of inertia is 2 pi R cube multiplied by thickness T, that is the throat thickness, which is same as equal to 2 pi R cube multiplied by throat thickness is equal to 0.707 multiplied by leg size equal to H. So if we apply the torsion formula, in that case we'll get T by J is equal to tau divided by R. Torque we are interested, so we have torque is equal to tau multiplied by J divided by R. So we have shear stress is given as 75. Polar moment of inertia is 2 pi R cube. So we have 2 pi. Radius is equal to 25. So we have 25 cube into 0.707 multiplied by leg size H, which is 12.5. Whole thing is divided by the radius R, which is equal to 25. So in this case the torque T will be equal to 2.603 into 10 to the power 6 Newton mm, that is close to 2603 Newton meter. So answer is 2603 Newton meter. The torque T that can be applied if the permissible shear stress is 140 megapascal. We have given here the leg size H is equal to 6 mm. Diameter D is equal to 50 mm. Hence we have radius is equal to 25 mm. Value of tau allowed is equal to 140 megapascal. Polar moment of inertia is J is 2 pi into R cube multiplied by throat thickness equal to T is same as equal to 2 pi into R cube, and we have throat thickness T is same as 0.707 multiplied by H, that is the leg size. T you have to find out. So we can apply the torsion formula, that is T by J is same as equal to tau by R. We are interested in the torque, so we have torque is equal to shear stress multiplied by J divided by radius of the shaft equal to R. Shear stress is equal to 140 megapascal. Polar moment of inertia is 2 pi. Radius of the shaft is equal to 25. So we have 25 cube multiplied by 0.707 times the leg size h, which is equal to 6, divided by radius of the shaft, which is equal to 25. So in this case we get a torque is close to 2.332 into 10 to the power 6. Answer will be in Newton mm. So in this case our answer is 2332 Newton meter. A circular rod is connected to the rigid plate by a parallel fillet as shown in figure. What will be the bending moment on the rod, that is the value of m you have to calculate, if the maximum bending stress, that is sigma b maximum, is equal to 75 and the throat thickness is given. Directly the value of t is given and the diameter of the rod is equal to 50 mm. So we have diameter of the rod is equal to 50 mm. The radius r will be equal to 25 mm. Throat thickness is directly given is equal to 5 mm. Maximum value of the bending stress sigma b max is equal to 75 megapascal. Value of m you have to calculate. The moment of inertia for thin ring is given as pi into r cube multiplied by throat thickness equal to t. Since the circular rod here is subjected to moment, we have to use the flexure formula. By flexure formula we have bending moment m divided by I is equal to maximum value of the bending stress which occurs on the outer fiber, which is at radius equal to r. The throat thickness is neglected. M value you have to calculate is same as sigma b maximum multiplied by moment of inertia I is divided by the radius of the rod is equal to r. Maximum bending stress permissible is 75. Moment of inertia is pi into r cube and we have r is 25. So we have 25 cube multiplied by throat thickness equal to 5 divided by the radius of the shaft is equal to 25. This answer will come in Newton mm. So we have bending moment will come out to be 736,310 Newton mm. Dividing by 1000 you will get the bending moment equal to 736.3 Newton meter. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.